Assalamualaikum and a very good day to all fellow researchers. I am Syafirah Zambry from Institute for Research in Molecular Medicine USM. Today I would like to share our research collaborate with SIDEC, School of Biological Science and School of Chemical Science, which entitled a printed circuit board label-free miniaturized electrochemical DNA sensor to detect SARS-CoV-2. The current pandemic COVID-19 was threatening the world by giving serious impact on public health sector, which subsequently affecting the socio-economic aspect along with the national financial policies. Due to that, presently there are many diagnostic methods available for the early detection of SARS-CoV-2, and amongst the method, the quantitative volatile RT-PCR has been widely used by healthcare workers to screen this contagious disease. Although this method provides highly sensitive and reliable results, they are not preferable for rapid on-site diagnosis. This is due to some few restrictions such as tedious sample preparation, their laboratory-based protocol, the requirement of sophisticated instrument, expensive reagent, and long analysis time. As alternative for that, the electrochemical biosensor could overcome the limitation since it can provide quick detection of viral disease with high selectivity and sensitivity. The implementation of electrochemical biosensor for the semi-quantitative and quantitative analyzing the respiratory virus has been proven due to their intrinsic characteristics such as simplicity, easy to operate, easy to miniaturized, which is they have miniaturized instrumentation, high portability with minimum power requirement, and low cost production due to the use of low volume of reagent and sample both in development and application. Because of this characteristic, it allows the electrochemical biosensor used as a point of care clinical diagnostic. Here is a brief idea on the electrochemical biosensor, where it is a biosensing device that transforms biochemical reaction between biological recognition molecule and analyte into measurable signals via current or voltage that controlled by potentiostat. The generating electrical signal here was proportional to the concentration of analyte in the biochemical reaction. Here are some examples of biological recognition molecule and analyte that most commonly used in the fabrication of the electrochemical biosensor. Basically, the well-fabricated electrochemical biosensor were mainly determined by the selection of the most sensitive biological recognition molecule and electrode fabrication. The implementation of the viral electrochemical biosensor for SARS-CoV-2 detection has been proven, and here are some reports. However, most of the research are focusing on the fabrication of the sensor based on immunoassay. But these methods are generally less sensitive compared to the nucleic acid test, as in the early stage of viral infection, the human immune system may not be active and could cause a false negative diagnosis. Therefore, in this objective here, in this work here, we try to develop a label-free miniaturized electrochemical sensor based on nucleocapsid gene for SARS-CoV-2 detection. Here, we will functionalize the working electrode with an A probe. Then we'll expose the probe to the target DNA and confirm the hybridization to electrochemical measurement. And lastly, we evaluate the detection time of the sensor. This is the design of miniaturized sensor that we use in this work, which is we apply our own lab-on printed circuit board, or we call as lab-on PCB based electrochemical platform that is done by our group at SIDEC USM, and this is their study, which is they have done study on miniaturization and optimization of the fabrication of this sensor. And basically, the sensor adopt the conventional 3-electrode system that made up of gold. This study also was confirmed the functioning of this electrochemical behavior before attachment with analyte and receptor. So here in this work, we use the optimized design of this sensor to develop lab-on printed circuit board based on SARS-CoV-2 nucleocapsid gene detection sensor. And this is the information of DNA sequence that we use for DNA probe and target DNA in this work. This show the overall flow for the fabrication of the PCB label-free miniaturized DNA sensor, which is basically the fabrication was started by immobilization of the dilated DNA probe into the surface of working electrode using a drop casting method. Then after immobilization, 6-mega-1 hexanol was added into the electrode surface to fill the unattached area and reduce the non-specific absorption of DNA probe. Then the sensor will expose to its target DNA to form a double-strand DNA. In this work, each step of fabrication was confirmed and characterized using cyclic voltammetric and electrochemical impedance spectroscopy in potassium ferricyanide as a redox probe. Here is a CV measurement and EIS measurement for the surface functionalization of gold electrode with the DNA probe. And if we can see from the bare gold here, the peak current here was used as the baseline current for the fabrication of DNA sensor in this work. And when dilated DNA probe was added into the bare gold working electrode, the peak current here significantly decreased due to the coverage of electrode surface by single-strand DNA, meaning that the addition of dilated DNA on the surface of electrode will blocking or inhibit the potassium ferricyanide ion to reach the electron surface, and also it reduces the electron transfer. Further addition of 6-mega-hexanol into the surface of electrode will further decrease the peak current due to the additional barrier between the redox mediator and electrode surface. In EIS here, the semicircle represents the electron or charge transfer resistance at the electron surface, meaning that the bigger the diameter of the semicircle here, the higher the charge transfer resistance at the electrode surface. As we can see from the EIS graph here, it was in line with the CV measurement where the semicircle increases when the dilated DNA probe and 6-mega-1 hexanol was added into the electrode surface. So the CV and EIS result here prove the successful of fabrication for this sensor in this work. Next, the electrochemical detection was started by exposing the DNA probe to the target DNA. In this work, as a preliminary study, we used target DNA with concentration of 1 micromolar. And here is the result. As you can see from the peak current here, the peak current decreased after probe DNA was hybridized with DNA. Similar with the EIS, where the largest semicircle here was found when DNA probe was exposed to the target DNA due to the more resistance exists on the surface of the sensor. And both of CV and EIS here support that the fabricated DNA sensor in this work successfully detect the target DNA. Then, in order to have a highest sensor response in a shortest detection time, we evaluate the DNA probe in different hybridization time, which is between 2 minutes until 1 hour. And as we can see from the peak current here, the lowest peak current was found at 5 minutes of incubation time. Similar with the EIS measurement here, where the largest diameter semicircle was found at 5 minutes. And if we notice here, when the sensor was exposed and incubate with the target DNA at hybridization time at 10 minutes until 1 hour, the semicircle trend here is almost similar and lower than 5 minutes. It could be because the evaporation of target DNA on the surface of miniaturized sensor during detection during the incubation time, as we use the drop casting method in this work. So here it was suggested that the maximum response of the sensor was found at 5 minute incubation time. As a conclusion in this work, it showed that the successful fabrication of lab on PCB based on SARS-CoV-2 nucleic acid gene, then the fabricated sensor could detect the target DNA within 5 minutes of incubation time, and this result demonstrate that the fabricated sensor could potentially be used as a precise platform for rapid, simple and portable sensor for detection of COVID-19. So therefore, in the next ongoing study, we will determine the limit of detection of this sensor. Before I close my presentation, I would like to thank to USM Research University grant and Ministry of Higher Education Malaysia for funded this research. Thank you.